All right, let's get right into it. We've all been there, right? You ask an AI a pretty simple question, and what you get back is a confident, super detailed, and just completely wrong answer. We call it hallucination, and honestly, it's one of the biggest hurdles to actually trusting these things. But what if it's not some random glitch? What if it's actually a predictable result of the exact way we train and test them? So that's the big question, isn't it? Why are these models so incredibly good at just making stuff up with a straight face? Why can't they just say, you know what? I don't know. It's a problem that hits even the top of the line systems, and figuring this out is the key to ever really fixing it. And this quote from the research paper, it just nails the perfect analogy for this whole explainer. I want you to think of a large language model like a student who's taking a really, really hard exam. When they hit a question they don't know, what's their best move? Well, it totally depends on how that test is being scored. And here is a perfect, almost painful example of this problem in the wild. The researchers asked 3 of the world's best models for the title of one of the author's dissertations. Just look at these results. You've got 3 different, totally plausible sounding and completely made up answers. The correct answer, none of them. They're not just wrong, they're creatively wrong. And that, in a nutshell, is hallucination. So where do these errors even come from? Well, this paper argues they start right from the very beginning. They're statistically baked into the pre-training process itself, even if you started with perfectly clean training data. To explain this, the authors did something really clever. They reframed the whole problem. So instead of thinking about generating all this complex language, they simplified it way down to a binary choice they call the is it valid problem. For any given sentence, can the model learn to just classify it as either true or false? This simple trick lets them bring all the tools of classic machine learning theory to bear on the problem. Okay, so first up, you've got problems that are pretty easy for a model to learn. A great example is spelling. There are clear rules, there are clear patterns, and a good model can easily learn to separate the right examples from the wrong ones. Simple enough, right? But then, you've got what the paper calls poor model errors. This is what happens when the model's basic design just isn't a good fit for the job. A classic example is counting the letters in a word. Early models were terrible at this because their whole architecture, based on tokens, just wasn't built for that kind of detailed, character-level task. It's kind of like trying to draw a perfect circle using only a straight ruler. But this is the one that's absolutely crucial for understanding hallucinations. What do you do with totally arbitrary facts, like someone's birthday? There's no secret pattern to learn there. The right answers and the wrong answers are all just jumbled together. The only way for the model to get these right is if it's seen them before and straight up memorized them. If a fact isn't in the training data, the model has no choice but to guess. And this leads to a simple but really powerful mathematical finding in the paper. They actually prove that a model's rate of generating errors is guaranteed to be at least double its rate of failing that simple is it valid classification. So what does that mean? It means even a tiny bit of confusion about what's true or false will explode into a much, much bigger number of actual errors. So it all boils down to how often a fact appears. Models are fantastic with things like Einstein's birthday because they've seen it a gazillion times. The real issue is what the paper calls singletons. These are facts that show up only one single time in all of that massive training data. And for these super rare, hard-to-memorize facts, the math is clear. The model is statistically guaranteed to mess up. Now, this right here is a real eye-opener. On the left, that's the base model, right out of pre-training. And look at it. It's beautifully calibrated. Its confidence pretty much matches how accurate it is. But now look at the chart on the right. After we fine-tune it with human feedback to be more helpful and conversational, its calibration is a complete mess. It becomes wildly overconfident. The very process we use to make these models better is actually making them worse judges of what they know. Okay, so that brings us to the second half of this mystery. The errors are baked into the training, we get that. But why do they stick around? Well, the paper makes a pretty bold claim here. The very tests we use to grade these AIs are a huge part of the problem. We are basically rewarding them for bluffing. So let me ask you this. What's the penalty for guessing wrong on one of the big AI benchmarks? The answer? A big fat 0. Nothing. A correct answer gets a point, and a wrong answer, or saying I don't know, gets you 0. In a system like that, what's the smartest strategy? You guess. Every single time. And you don't have to take my word for it. This slide right here is basically the smoking gun from the paper. It's a list of the biggest, most important benchmarks in the AI field. Just look down that third column.
Almost none of them give you any credit at all for admitting you're not sure. The entire evaluation system is set up to reward the student who takes a wild guess over the one who honestly says, I don't know. So the paper's argument is crystal clear. We have what they call an epidemic of penalizing uncertainty. We are optimizing our models to be fantastic test takers who know how to game the system for a high score, not to be trustworthy partners who actually understand the limits of their own knowledge. Okay, so if the test is the problem, then how do we fix it? Well, the paper proposes a solution that's actually beautiful in its simplicity, and it's borrowed straight from high-stakes tests that we humans take. Here's the plan. We just change the scoring. A correct answer? You still get a point. Saying I don't know? You get 0 points. No harm, no foul. But, and this is the key, a wrong answer now gets you a penalty, like -1 point. This is exactly how exams like the old SAT used to work to stop people from just randomly guessing. And the effect of this one simple change is huge. It completely flips the whole incentive structure on its head. All of a sudden, bluffing is a terrible strategy. Now the model is forced to actually do a little cost-benefit analysis based on how confident it feels. And we, the people running the tests, can actually tune that penalty to make the model more cautious or more daring, depending on what we need it for. And here's the really smart, strategic part of this idea. The authors argue that we shouldn't just go off and build some other small niche hallucination benchmark that nobody uses. No. To really change the whole field, you have to change the rules of the main event, the big, popular leaderboards that all the major labs are already competing on. That is how you get everyone to start caring more about honesty than just getting a high score. And that leaves us with this final question, which really gets to the heart of this entire issue. Right now, our evaluation systems are pushing us to build better and better test takers. But maybe, just by changing the rules of the test, we can finally start building the trustworthy, reliable AI partners that we actually want.